Hey everybody, welcome to our lesson on standard deviation. First thing we're going to take a look at here is a question from your homework. So in this part of your homework we were talking about Connie and Oscar, and these were their scores. And you can see what you should have found is that the mean is 84 for both of them and that the median is 84. But you can definitely see that their test scores, or whatever they are, vary a lot more than what they look like right there, than what their mean and their median is showing. So when you take a look here, it says your mean and median values aren't showing the true differences between these two data sets. So we can talk about how each test score deviates from the mean, so how far away from the mean it is. So we're going to find the average of these two deviations. So pause the video, go ahead, find the average of the deviations. And what I mean by a deviation is how far away from the mean. So pause the video, find your deviations. Welcome back. If you take a look here, take all my ink off my page, your deviations here, 82 minus 84, that's how I got my -2. 84 minus 84 here, that's how I got my 0. And then down here with Oscar, 72 minus 84 is -12. When you add all of these deviations up, even though you can see down here that these deviations are further away than these deviations here, they still add to 0. So what's actually happening here is what our concept is for standard deviation. Okay, we're going to have a formula here. It's a little bit different than what we did, but it's the same idea. So if you take a look here, standard deviation simply provides a way to judge the average distance between the data values and the mean. It's a measure of how the data are spread out around the mean. So everything for standard deviation is in relationship to the mean. So this thing S right here, this is our standard deviation. This symbol here is sigma, means to take the sum, add them all up. This symbol here, x sub I, means the individual data value. This one we know as x bar, which is the mean, and n is the number of data values in the set. So now when I reveal this formula here, please don't freak out, it's not that bad. We're just going to take each of these parts step by step. So, standard deviation is the square root of the sum of our data points minus the mean squared, all divided by the number of pieces of data minus 1. So we're going to try a couple of these. Taking a look here, you're going to find the standard deviation of this data set right here, 2, 4, 7, 8, 12, 15. First step, you're going to find the mean. So take a moment, find the mean. Okay, your mean there is 8. Then you're going to find your deviations from the mean. So you're going to take your data point, your 2 minus 8 is -6. And then you're going to square that, 36. So take a moment, finish up the rest of this table, and then we'll work through the rest of the equation. Okay, so looking here, that wasn't what I wanted to do. We're going to erase here. You should end up with -4 and -1, 0, 4, and 7. So when you square those, you're going to end up with 1, with 0, with 16, with 49. Then what this means right here is it means take your data value minus the mean, which we've done here, square them, which we've done here, and now we're going to add them all up. So when we do that, we get 118. Looking back at our formula here, we're going to take the square root of the sum of x minus x bar squared divided by the number of pieces of data minus 1. So when we look at the rest of this, we're going to go ahead and plug this in. Oops. We end up having 118, which is right there, divided by 6 minus 1 because we had 6 pieces of data minus 1, so that's 118 divided by 5. So the square root of 23.6, and we get a standard deviation of 4.86. So what does that mean? That means that the average distance away from the mean here of 8 is 4.86. We're going to look at standard deviations now of Oscar and Connie's scores. So when we do this, this is Connie. Connie had a mean of 84, if you recall. And we type all those in, or we write them in. You can see that Connie's standard deviation is a very small 1.53. If we do the same thing with Oscar's, again, all of our data points, data point minus the mean, square them up, Oscar ends up with a standard deviation of 9.59. So when we take a look back at what their original scores were, you'll remember that Connie's scores were a lot more consistent than Oscar's score, and we finally have a way to measure that, or to show that, because the mean didn't work and the median didn't work, but now, lo and behold, our standard deviation does show us that Oscar's scores are more spread out than Connie's. So try this one on your own. Find the standard deviation of this set here, 20, 25, 30, 40, and 80. Set up your table, find your mean, plug it all in, pause the video, and then come on back. Welcome back. You should have gotten a mean of 39. That's what your table should look like. You should get a standard deviation of about 24.08. Hopefully you got that correct. If not, take a look through here, see where you made your mistake. So now, how do you do this using your calculator? Well, it's actually not that bad. You're going to enter all of this data into your list 1. So you're going to go stat, edit, put it in list 1. Second mode, remember that's the only time in math I let you quit, is when you do second mode on your calculator. Then you're going to do stat, calc, 1var stats, press enter, and then our standard deviation is S sub x. That's what we're going to be looking for there. Okay, so that's how you do that on your calculator. And so what does standard deviation really mean? Well, if you recall from the definition, it's the average distance between the data values and the mean. So what does it mean in English? So it means a large value for standard deviation means that the data values are not as tightly packed around the mean. So a big standard deviation is not very close to the mean, whereas a set with more data near the mean will have less spread and a smaller standard deviation. What you should notice is that because standard deviation is the average distance the data is from the mean, when the data in a histogram or another graph is flat, it has a large average distance from the mean. But if the data has a bell-shaped curve or a normal curve, looks a little something like this. You've probably seen it before. Much more of the data is closer to the mean in here, and then your standard deviation is lower. And we'll do much more with that in our next video. Controversy. Ooh, exciting, isn't it? Some statisticians don't agree on why we divide by n-1, although they almost all pretty much agree that we should. So here's one reasoning. It's actually in your textbook, which you guys probably haven't seen this year, but we do use a textbook. Anyway, in there it says, you may wonder why you divide by n-1 when calculating standard deviation. As you know, the sum of the deviations is 0. So if you know all but one of the deviations, you can calculate the last deviation by making sure the sum will be 0. That last deviation depends on the rest, so the set of deviations contains only n-1 independent pieces of data, because you've still got that other one left there. There are 2 types of standard deviation. We are only using one of them in our class, but there's a sample standard deviation, which is what we use. That's our S sub x. It divides by n-1. It's what our calculator does for standard deviation. However, if you take AP Stats, you're going to be using population standard deviation. it divides by n instead of n minus 1. And there's a listing for this in your calculator also, but we're not going to be using that one. We're, again, going to just be using this s sub x. So when you're looking for standard deviation in your calculator, make sure you're using this one, okay? All right, outliers. We have two definitions of outliers. One of them is 1.5 times the IQR, and then you add that to Q3 or subtract it from Q1. But there's another definition of outlier that now that we know what standard deviation is, that's what we're going to use. It's 2 times the standard deviations away from the mean. So values that are more than 2 standard deviations away from the mean would be considered an outlier. Affected by outliers versus not affected by outliers. Your mean, your standard deviation, and your range are all affected by values that are way away from the rest of the data set. Things that aren't affected by mean would be your median, your mode, and your interquartile range. Standard deviation is affected by outliers because the mean is affected by outliers. Your interquartile range is not affected because your median is not affected. Percentile rank of a data value gives a percentage of data values that are strictly below the given value. So if Ellen scored in the 85th percentile on her standardized test, what does that mean? Well, that means that 85% of the people that took the test scored below her. If you take a look here, we've got these shoe sizes of 14 students. You're going to find the percentile rank of size 11.5 shoes. So what you do to find that is you count how many pieces of data are below 11.5. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And you divide that by 14. So that's going to be 9 divided by 14 would be your percentile rank there. 9 divided by 14. Okay, then the percentile rank of size 9 shoes. 1, 2, 3, 4 divided by 14. What shoe size is at about the 57th percentile? So what you're going to do there is you're going to take your 0.57 and you're going to multiply that by 15. So 0.57 times 15. I don't know if this is going to work on here. It's probably not going to work on there. 0.57 times, not 15, 14. Hold on a minute here. Pulling the old calculator out. 0.57 times 14. We are going to be looking for about the 8th data value. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 values below that would mean that a size 11 is at the 57th percentile. And what shoe size is that about the 10th percentile? Well, if I take my 14 times 0.10, that's 1.4. That means there's 1.4 data values below. So we're going to round that to 2. So a size 7 here would be about the 10th percentile. Okay, not perfect on that one, but you get the idea. Finding percentile rank from a histogram. What's the percentile rank of a 75-foot tree? If you look here, here's 75 feet, and if you recall, your histograms, remember if this data value that's on the edge here goes into the box at the right. Okay, so 75 is actually in this box. So if we look here, we've got 3 plus another 3 plus an 8 plus a 10 plus a 5 plus a 2. So that's 6, 14, 24, 29, 30, 31. So we have 31 trees there. And how many of them are below a 75-foot tree? Well, 75 is in here. We've got 8 plus 6, that would be 14. So 14 data points below the 31. Or if we calculate that out, that would be about 0.45. So the 45th percentile approximately. 45th percentile. Boy, that looks terrible. Sorry about that. In which percentile is the 40th percentile? Or sorry, which interval is in the 40th percentile? Well, if this is where your 45th percentile is, your 40th has got to be in here. So we're going to call that 70 to 74. Okay, so what you need to remember about percentile rank is it's the number of values strictly below where you